Hi everyone, my name is Dmitry Semenok. I'm the first co-author in this paper, novel strongly correlated europium superhydrides. Within this work, we extended a series of investigated superhydrides of lanthanoids by three novel compounds. It's a cubic and hexagonal europium H9 and cubic PM3N clutterate zintal phase europium Eu8H46, which gives better explanation of the experimental equation of states than previously proposed europium H5 with the same symmetry group. Currently, superhydrides were discovered in 4 lanthanide hydrogen systems. It's a lanthanum, cerium, praseodymium, neodymium hydrides, and this work is related to europium. Europium is unusual lanthanoid. It has abnormally high atomic radius, which affects stability of ideal clutterate-like hydrogen sublattice and phase transitions between hydrides. Another interesting fact is that pure europium is a superconductor and loses its magnetic ordering at low temperatures. As I will show on the next slides, this can happen with europium superhydrides too. I would like to start from dynamic stability of compounds described in the paper. When we first time calculated phonon density of states for ideal structures of europium monohydrides F43M europium H9 and a hexagonal P63 MMC europium H9, we were unpleasantly surprised that they are dynamically unstable and have many imaginary modes. Distortion of the ideal structures, of course, helps a little bit understand the situation, but not completely. Then we assume that the matter might be in the anharmonicity of hydrogen vibrations. Indeed, machine learning of interatomic interaction potentials based on the results of molecular dynamics showed that actually all studied europium hydrides are dynamically stable. This once again emphasizes the importance of taking into account anharmonic effects in the study of hydrides. We also studied magnetic ordering of europium hydrides. Ideal cubic and hexagonal structures of europium monohydride, europium H9, demonstrate antiferromagnetic and ferromagnetic ordering, respectively. Europium Eu8H46 possesses clear ferromagnetic ordering with high Curie temperature, 336. Interestingly, a slight distortion of the hexagonal structure of europium H9 to CM-CM space group leads to the disappearance of magnetic order and appearance of a kind of window for the manifestation of superconductivity. This is the first time for lanthanide hydrides where a detailed study of weakly distorted structure leads to the possibility of superconductivity. Distortions of ideal cubic and hexagonal structures of europium hydrides reduce the enthalpy of formation and bring those distorted compounds to the convex hull, closer than the ideal structures in both cases, with using Hubbard correction and spin-orbit coupling, and without Hubbard correction. We should note that, however, the europium superhydrides we found are somewhat higher than the convex hull. There may be several reasons for this. First, it's a non-stoichiometric composition of the synthesized hydrides, and the second reason is the quality of the potential for europium, which have never been tested for this pressure range, is unsatisfactory. This can also explain some deviation of the experimental equation of states from the calculated one. Due to the presence of magnetic order in europium hydrides, it's probably impossible to observe the superconducting transition in these materials. Instead of studying superconducting properties of europium hydrides, we studied the effect of the europium sublattice on the hydrogen sublattice, and found that this effect is extremely negative on both superconductivity and the density of electronic states. The only positive effect of europium atoms is stabilization of metallic hydrogen sublattice. Conclusions. Using ammonium borane as a source of hydrogen, we successfully synthesized a series of new europium superhydrides. It's a two modification of europium H9. It's a hexagonal and cubic modifications, and a PM3N cubic europium Eu8H46 at pressure range 86 to 130 GPa. These superhydrides may have distorted hydrogen sublattices. Such distortion of ideal clutterate-like hydrogen cages significantly reduces the enthalpy of formation of europium superhydrides. And anharmonic effects play an important role in dynamic stabilization of all discovered hydrides. Without accounting this effect, it's impossible to explain how these europium hydrogen phases can be stable. studying magnetic ordering in the europium hydrides, we found that small distortion of p63mmc to pseudohexagonal CMCM space group makes europium H9 non-magnetic. This could open the possibility of observing superconducting transition in this compound. And finally, investigation of europium H system is important because using nuclear resonance scattering on europium 151 may allow us directly determine their magnetic properties. Thank you for your attention.